Hey guys, this is your introduction to the Mpls programming assignment. It is available over here on GitHub. Okay, so let's see. So in this programming assignment, you will implement Mpls forwarding on routers. You will control the forwarding using Mpls labels. So in the last assignment, you controlled forwarding paths using link costs. Here we'll have another method using labels. And you will also implement priority-based forwarding on the routers. This is part of the quality of service or QoS mechanisms we talked about in class. Okay, so the starting code is has the same files, which is as in the last assignment, which is network.py and link.py, implementing network layer and link layer respectively. And we start also with this simple topology implemented in simulation.py. The one change to the implementation of this is that the link layer thread will forward traffic along links. However, the forwarding speed is being restricted by link capacity. Okay? So this will run a little bit longer as we actually take time to serialize each packet that is being transmitted. And I'll show you guys where that happens in the code. Okay? So then, to start a program, of course, it's Python simulation.py, and we set the simulation time to 10 seconds to account for the forwarding delay. Okay, so going on to the assignment. 3 parts. The first one is you will implement Mpls forwarding such that only links incident on hosts carry network packets and links between routers carry Mpls frames. So here, between the host sends a network packet to the router then will encapsulate that packet into an Mpls frame that gets forwarded between routers, and then the last hop router between to the destination host will decapsulate the network packet that's encapsulated by the Mpls packet and forward just the network packet onto the host 2 for receiving. Okay, so the host should never see or touch the Mpls packets. Those are only forwarded between routers. Okay, so 1A, you will implement an Mpls frame to encapsulate network packets as Mpls frames. Okay, so we're going to need a new class, which is very similar to the network packet class. This new class will encapsulate network packets. So this is here a picture from the network slides where we presented Mpls. Okay, so you have your Ethernet header, then your Mpls header, then your IP header, and then the IP payload. Okay? In this project, we simplify Ethernet as a link frame. Okay, so I added that class. And the link frame now will tell you whether or not it's carrying an IP packet or an Mpls packet. Okay. Okay, so reading along, link frame carries both Mpls frames and network packets, and a type S, type string, allows the router to figure out what is being embedded. Okay, so your link frame will either carry the Mpls frame, or your link frame will carry directly the IP header or network packet in our setup. Okay. So your task then is to implement the Mpls frame to encapsulate network packets. Again, this encapsulation will take place at the first hop router. Okay, and that will happen according to the rules defined in encapsulation table dictionary. Okay, so I'll show you guys where that is implemented as a parameter to router. Okay. You guys will be able to define what that structure is, and you don't have to implement all the different frames of Mpls. The only thing you need is really label, but if you want to play with the other parts, that is also acceptable. Okay. So now we have encapsulation. So we send a network packet, and the first router is going to encapsulate it into the Mpls frame that you implemented. Okay. So then down here in 1B, you will implement Mpls forwarding based on Mpls forwarding tables passed to the router as forwarding tables dictionary. Okay. So you need to define what these tables look like, and make sure that the router forwards packets according to this. Okay? So to do this, you will need to modify process queues and process Mpls frame, and I'll show you guys in code where this needs to happen. Okay? So then the final part 1C is you will implement Mpls Decapsulation at the last hop router to deliver network packets to hosts. Okay. The rules of when to decapsulate or what packet to decapsulate and how will be embedded in the decapsulation table dictionary. And again, that part is up to you to define how you want to structure this table. Okay. So going back up to our figure, part 1A creates an MPLS frame and then encapsulates network packets that come in from host to the router. Then part 1B implements forwarding based on MPLS between the routers, and then part 1C decapsulates the MPLS frames to deliver network packet to hosts. Okay. So you will submit separate code for this with subscript 1, and you will record a video showing the execution of this part of the code. Okay. So in part 2, you guys will implement MPLS forwarding on the different paths, just like in the last programming assignment. Okay, so what we want is that packets from host 1 follow a different path to host 3 than packets from host 2. Okay? So you need to configure MPLS forwarding tables such that the routers take this, implement this behavior. Okay? You will submit this as a separate set of files and record a separate video just for this portion of the code, just for this problem too. All right. So then in problem 3, your task is to implement strict priority forwarding between the different MPLS routers. Okay? And the way to do this is to recall that the IP header has a type of service field. Okay? So your first task is going to be to modify network packet to start carrying this priority. This is partially implemented in your starting code, and you guys need to extend a little bit so that this value is actually carried in the packet. Okay. So what's nice about this? Oh, and so let's just settle on the fact that higher priorities higher numbers represent higher priorities. Okay, so priority 1 is going to be higher than priority 0, which means that we would forward packets under strict priority forwarding. All the packets of priority 1 would be forwarded before any of the packets of priority 0. Okay, so in 3B, we will start playing with the network capacities. Okay? So if you run the original scenario simulation.py in here, you will notice that the capacity between router B and host 2 is smaller than the capacities on all the other links. So as traffic gets sent by host 1, it gets stuck in the queue at router B and then slowly offloaded onto host 2. Okay? So going back down, in 3B, your job is to implement this functionality in this network such that we get a bottleneck at router D of packets being sent from host 1 to host 3 and from host 2 to host 3. Okay. Okay, and then the last part of it, just so we know what's happening, is that you need to change the program output such that we can see how many different packets or how many packets of each priority are waiting at the router D in its queue to be forwarded to host 3. So for example, the output would say, okay, we have 2 packets of priority 1 and 3 packets of priority 2 waiting at router D for transmission. And the way to do this, the way to inspect that, to inspect how many packets are waiting, is you can inspect the priority encapsulated network packets. That is not the only way to do so, so you may do it in a different way. That is up to you. Okay, so then in part 3C, you will implement strict priority forwarding at each router. So if we have 2 packets of priority 1 and 3 packets of priority 2 stuck waiting at router D, then packets of priority 1 need to be forwarded first, right? It's not a FIFO queue. Okay? So the important thing is that in 2B, you were able to cheat by looking at the priority of encapsulated network packets. In MPLS routers, they shouldn't work like that. They should forward basically just based on what's in their forwarding tables, so just based on the labels embedded in the packet. Okay, so what I don't want you to do is to extend the MPLS header to carry the priority information, or to inspect the packet that's encapsulated. Okay, you will need to come up with a different method such that routers encapsulate network packets at the edge and forward them still on the different paths, and also forward them with strict priority. Okay, and this should be based purely on the information in the MPLS tables. All right. So, needless to say, you may need to modify those tables. Okay, so then you will submit length, sort of the same code with substitute 3, and a video showing the execution of simulation_3.py. Okay, and then we have 2 bonus assignments. One is to implement fair-weighted queuing instead of strict priority queuing. And the other one is to implement a centralized controller that will configure the MPLS tables in question 2, just to make things a little bit easier. Okay, so this is sort of like implementing an SDN controller for MPLS. All right, so with that, let us look at the code. So the starting code, let me make this a little bit bigger. Okay. Okay, so the starting code, of course, is simulation.py, where we start. We have 2 hosts. And here's the big change. We have the different tables and interface capacities. So first, looking at the router constructor, we are passing in interface capacity list, okay, which will say 500, 500. This is in bits per second, super slow links, just so we can sort of follow along as things are being transmitted. So what this means is that we have 2 interfaces, right? Interface 0 and interface 1. Okay, so if we look at the router, interface 0 is here, interface 1 is here. Their capacities are 500 each. Okay, if we look at router B, we have interface capacities 500 and 100. 500 belongs here, 100 belongs here. So this link is going to be slower, which means packets flowing from host 1 to host 2 will be stuck at router B. You will see that in the output. Okay, so then we look at the other parameters. So we have encapsulation table, forwarding table, and decapsulation table. And you will work with these in parts 1A, 1B, and 1C. Okay? You need to figure out what information needs to be stored in these tables and what is the format of these tables. That is up to you. I'm giving you guys more sort of leeway here as you are progressing in your ability to design network mechanisms. Okay, so these are 2 routers. Again, we add links, nothing new here. And there's one change here where we will send 5 packets from host 1, and we are alternating the priority in each packet, which is passed to UDT send as a parameter. Okay, so now the host can send packets at different priorities. Okay, let's look at the next file, which is going to be network.py. Okay, so the change here is that now your interface is going to have a certain capacity. We pass that as a parameter, and then it gets saved here. Okay. Get doesn't change. We still just get the packet that is queued on one of the queues of the interface, either the in queue or the out queue. Okay. Great. Okay. So nothing has changed here significantly. Okay. In the network packet, you'll notice that we're passing priority in here, but we don't do anything with that priority. So you will need to add something to carry that priority within the packet later on in part 3 of the assignment. Okay, let's see. Host doesn't really change, except that we are sending, when you're sending a packet, now we're sending a link frame instead of sending a packet, right? So I mentioned that your link frame will now either carry an MPLS packet or an MPLS header or an IP header, so an MPLS frame or an IP packet within the link layer frame. And so here we're saying that we're creating a link a link frame to transmit our data, and we're specifying that as that the contents is a network packet. Okay, same transmitted as before, and then in the UDT receive, we're checking that the frame that has been delivered to a host is of type network. Right. So in other words, when host 2 receives a transmission from router B, that MPLS frame has to be decapsulated so that only network packets are being processed by the host. So this assert enforces that. Okay. Okay, so then let's look at the router. We have all the different interface capacities that are being saved. So when we create interfaces, we're going to pass the capacity into that interface, and we're saving the different MPLS tables in here. Okay, so the biggest changes happen here under process queues. So each time router tries to pull out a different packet, first it's going to pull out a frame, not a packet, right? Because we either have MPLS or link layer frames that either carry an MPLS frame or a network packet. So depending on the payload of the frame, we're either going to process a network packet, so then we call the process network packet function, or if it's an MPLS frame, okay, then we're going to call process MPLS frame. What happens now is you guys we haven't still implemented the MPLS frame class, okay, and so we're just going to set the MPLS frame variable equal to the packet. Okay, and just pass that into the MPLS frame. So instead of passing a proper MPLS frame, we're passing a packet that we, just assume or sort of cast it as an MPLS frame. Okay. So what we have there is the process network packet and process MPLS frame. All right. So this is important because when we first get a network packet from the host, that packet arrives at the router, and it will fall through here, process queues. The router will say, okay, this is a network packet, and we're going to process network packet. And here, you will implement the encapsulation of the packet as an MPLS frame. Okay? And once you do that, then you will have an MPLS frame, which you will pass to process MPLS frame. Okay? So a network packet becomes an MPLS frame, and then gets passed as MPLS frame to forwarding functionality to be forwarded. And so sort of it gets processed twice at router A. So then in process MPLS frame, you will want to either forward that packet, or if you're at router B and you receive an MPLS frame, you want to decapsulate it. And this is for you to implement. For now, we're just forwarding everything out interface 1, just so it makes it to the end. Okay, so that's it for network.py. Let me back us up. Okay, and here we go to link.py. The biggest change here is that we are now forwarding, we have a link frame class, okay, which is going to either carry MPLS packets or network packets. Okay, so that's the change there, and you have the usual to-byte and from-byte methods. Okay. Then in the link frame, when we do a transmission, we're going to check the next available time at which packet can be transmitted. Okay. So basically, after we transmit a packet, we can say that according to the speed of the link, it's going to take some time for that packet to be transmitted, and so the next packet cannot start its transmission until next available time. And so this is the switch to make sure that packets wait for their turn. So we get a packet from the out interface and then try to put it to an in interface. Then we look at the packet size, multiply it by some number of bits, okay, and then we calculate the next available time as the current time plus the time it takes to serialize those bits according to interface capacity. So you will see this in the output that we're transmitting a packet, there's next available time, and you can also see the queue size of the number of packets that remain queued. Okay, and so that's it. The rest of the link layer does not change. Okay, so that is it, and good luck.